In October 2015, we flew the SkyTEM system over the Tulare Irrigation District in California's Central Valley. What did we want to do? We wanted to see beneath the ground to map out the distribution and connectivity of the various sediment types, the sands and gravels, the clays. The SkyTEM system is an airborne time-domain electromagnetic system that maps out sediment type by measuring the electrical resistivity of the subsurface. So what you're seeing here are the SkyTEM technicians at a local airport getting the system ready to attach to the helicopter. There is the large transmitter loop through which current flows, setting up a primary magnetic field. This generates eddy currents at various depths beneath the ground that in turn set up secondary magnetic fields measured by the receiver. At the back you can see mounted on the transmitter loop. Now there's a boom out the front extending from the transmitter loop. At the end of that is a magnetometer that provides magnetic data. So this is the SkyTEM system taking off, and the cheer was me thrilled that this was actually happening. So here we are zooming in on the Central Valley, zooming in on the Tulare Irrigation District in the San Joaquin Valley. What you're seeing here is a display of the resistivity values that were extracted from the data through inversion. We have the Google Earth map at the bottom of the image to keep track of location. So it looks like all the resistivity values are above the ground surface. That's not the case. At every location where we acquired geophysical data, we've displayed the resistivity values as a cylinder, color-coded to show how electrical resistivity changes with depth. So each cylinder starts at the ground surface and then extends to a depth of, on average, 500 meters. So we were able to see 500 meters beneath the ground surface. The cool colors, the blues, indicate low resistivity materials. The warm colors, the reds, indicate high resistivity materials. And again, the Google Earth map lies beneath the display of resistivity values just so we can see where we are. Now we transform the resistivity values to the sediment type that is present at that location. We developed this link, allowing us to go from resistivity to sediment type using data from locations where we had both our geophysical data and lithology information from wells. The low resistivity units correspond to clays, shown in blue here. The high resistivity units correspond to sand and gravel, shown in yellow. And in between, the green indicates mixed coarse and fine materials. So we'll start with this three-dimensional model where we've interpolated between our measurement location to get a full 3D representation of sediment type in the subsurface. And what we're going to do now is slice through this volume. So looking at 2D slices. And what we can see, the blue again is the clay, the yellow is sand and gravel, the green is the silt, and we can see the variation in the distribution of these sediment types as we move through this area. We were really thrilled with what we were able to achieve with this three-dimensional imaging of the subsurface using our airborne geophysical method. We were able to see below the ground surface to a depth of 500 meters, mapping out in incredible detail sediment type. Where's their sand and gravel? Where's their clay? And this is exactly the sort of information that we need to model groundwater systems, to understand the movement of the water and to identify areas where there are connected pathways of sand and gravel that could be used to recharge the aquifers at multiple depths. Geophysical imaging such as this can provide the essential data that we need to support effective and sustainable groundwater management.